Hello, everyone. My name is Wenbo, and I'm a PhD student from Professor Zubin Jacobs' group at Purdue University. Today, I will discuss limits to two-spin-qubit gate fidelity from vacuum and thermal fluctuations. Here is the author list and our context. I want to begin with a question. Since recent demonstrations of quantum gate operations have observed increasing fidelity, do we still need to further increase the quantum gate fidelity? The answer is yes, and I want to address this question from an error correction point of view. Error correction refers to the process of mitigating error due to quantum uncertainty in the quantum computer. On the left of this slide, we show a schematic of a popular error correction method, surface code, based on silicon quantum dot qubits. We can see the physical qubits here, and also the metallic lines that are important for qubit manipulation in this figure. Error correction has the advantage of large tolerance to local error rate for physical qubit. It is also very efficient in qubit scaling up. However, surface code complexity and quantum computer size is sensitive to physical qubit fidelity. We show the relation between error correction complexity and physical qubit fidelity more directly in the next slide. Logical qubit is the basic building block of a quantum circuit. Surface code offers a way to build one logical qubit from multiple physical qubits. In the left figure, each circle represents one physical qubit, and each purple box represents one logical qubit that consists of multiple physical qubits. So more physical qubits are needed to build one logical qubit if the physical qubit gate fidelity is low, as is shown by the growing purple box. Quantitatively, take quantum Shor's algorithm, for example. It requires logical qubit error rate as low as 10 to minus 15. In this case, if we could reduce the physical qubit error rate from 0.1% to 0.001%, then we can reduce the number of physical qubits needed to build one logical qubit by over 10 times. Next, we discuss different environmental sources that can decrease quantum gate fidelity. In the left, we show a schematic of a quantum computing device based on spin qubits and 4 different sources of noise. We show their corresponding noise and optimization methods on the red table. For instance, nuclear spin noise coming from isotopes with non-zero nuclear spins can decohere spin qubits. This is solved by using isotope-enriched material. Unstable microwave pulses may cause gate fidelity decrease and can be solved by Hamiltonian engineering. Fluctuating charges in the vicinity of semiconductor quantum dots can lead to charge noise, and symmetric operations can solve part of this problem. In contrast, the influence of thermal and vacuum fluctuations of electromagnetic fields on quantum gate fidelity is not well studied or evaluated. So in the following, we are going to first introduce the evanescent wave-Johnson noise caused by thermal and vacuum fluctuations. Then we will investigate its role in quantum gate fidelity. Finally, we will propose a corresponding optimization method, which is Lindblad engineering. So thermal and vacuum fluctuations of electromagnetic fields come from quantum degrees of freedom. Imaginary part of decoherence function describes thermal and vacuum fluctuation strength, and qubit relaxation time is inversely proportional to imaginary part of decoherence function. Since evanescent surface and bulk waves in metals provide additional degrees of freedom for electromagnetic fields, and they can enhance thermal and vacuum fluctuations in the vicinity of metals. Therefore, we call the noise caused by thermal and vacuum fluctuations in the vicinity of metals as evanescent wave-Johnson noise. And the spin qubit system dynamics can then be described by the Lindblad master equation. To this end, we want to show different quantum computing devices in several different systems. One common theme we can observe is that they all rely on metallic gates for quantum operations, and the metals will intensify evanescent wave-Johnson noise in the device. Therefore, evanescent wave-Johnson noise commonly exists in a wide range of quantum computing systems. Here, we show experimental evidence of relations between spin qubit relaxation time and evanescent wave-Johnson noise. The left figure shows that in NV centers in diamond, the experimentally measured relaxation time changes as a function of distance from metal contacts due to evanescent wave Johnson noise. The red figure shows that in most devices, the spin-qubit relaxation time is also dominated by evanescent wave Johnson noise in the low magnetic field region. In this slide, we present the theory model we are going to use for system dynamic simulation. I will just briefly go through this slide. So first, we use Lindblad master equation to describe system dynamics. Then we present the closed quantum system Hamiltonians and the Lindblad superoperators for two popular quantum computing systems. One is NV center in diamond, another is silicon double quantum dot. So thermal fluctuations will induce spin-qubit thermally activated stimulated emission, and the strength depends on the mean photon number in the environment. So, and also both thermal and vacuum fluctuations are related to the their strengths are related to the spontaneous emission rate, which is gamma E. So in this slide, we present the evanescent wave Johnson noise influence on CNOT gate fidelity in silicon dot system. The system consists of two electron spin qubits in silicon double quantum dot. We simplify top gates and antennas to an aluminum thin film. We also consider non-locality in aluminum, and this non-local response is largely determined by the electron collision frequency nu. So here we show two color maps, and the color represents the CNOT gate fidelity decrease due to evanescent wave Johnson noise. In the left color map, we consider only the influence of vacuum fluctuations, and we study its dependence on the material property, which is determined by electron collision frequency nu in aluminum, and also its dependence on distance between the electron spin and the aluminum thin film. In the red color map, we present the influence from both thermal and vacuum fluctuations, and we also study its spatial and temperature dependence. In this slide, we present evanescent wave Johnson noise influence on CNOT gate fidelity in diamond NV center system. So here, the system consists of one electron spin and one carbon-13 nuclear spin. We still simplify top gates and antennas to a silver film. Here, we are considering a local model to describe the dielectric property of silver. As a result, we only need to consider silver permittivity epsilon. So similarly, we show two color maps, and the color represents the CNOT gate fidelity decrease due to evanescent wave Johnson noise. In the left color map, we show the influence from vacuum fluctuations only. We study its dependence on the distance between electron spin qubit and the silver film, and also its dependence on the silver material property, which is represented by imaginary part of permittivity. In the red color map, we present the influence from both thermal and vacuum fluctuations, and we study its spatial and temperature dependence. After we identify influence of evanescent wave Johnson noise, we consider optimization method to suppress its influence. So the left figure represents a schematic of Lindblad engineering. Rho I and rho F represent the initial and final density matrices of the spin qubit system. The post 1 to post k are used to realize the quantum gate operations. The system dynamics, which is represented by this twisted arrow, is influenced by Markovian noise from environment during this process. And we take the post parameters from post 1 to post k into a vector x, and x here contains the amplitude, phase, and the length of all the control microwave pulses. So through the system dynamics for given spin qubit T1 and T2 time, we can obtain a function that connects the pulse parameter vector x and the gate fidelity f. And in Lindblad engineering, we search for optimal pulse parameter x that can maximize the gate fidelity. So this is a nonlinear optimization problem with constraints, and we can solve this by the interior point method. So in this slide, we present the application of Lindblad engineering in Diamond evanescent system. We show 3 different microwave pulse sequences. The first comes from the literature. The second is optimized by Hamiltonian engineering, and the third is optimized by Lindblad engineering. So here we show the pulse parameters of the 3 microwave pulse sequences in the 3 bar plots in the top half of this figure. So here, each microwave pulse sequence contains 3 microwave pulses within 4 delays. Tau and phi are the length and phase of the 3 microwave pulses, and t represents the length of the 4 delays. So here we can find that only in the case of Lindblad engineering, we can realize the largest high fidelity region. This means that we can obtain a microwave pulse sequence that is more robust against thermal and vacuum fluctuations in Lindblad engineering. In this slide, we present the application of Lindblad engineering in silicon quantum dot system. Here we compare the result from Hamiltonian engineering and Lindblad engineering. Since only one microwave pulse is used to realize CNOT gate operation, the pulse parameters X contain only 2 variables, which is the strength of the microwave pulse, omega, and the length of the microwave pulse, T. Similarly, we can still find that high fidelity region is larger in the Lindblad engineering case. However, since there is only one microwave pulse, Lindblad engineering can only give a quite straightforward solution, that is to reduce the length of the microwave pulse. This also indicates that Lindblad engineering may be more powerful and effective in designing complex microwave pulse sequence. So to summarize, we first investigate evanescent wave Johnson noise influence on CNOT gate fidelity. We study its spatial and temperature dependence and its relation to dielectric response property of metallic contacts. Then we propose Lindblad engineering method to mitigate evanescent wave Johnson noise influence on quantum gate fidelity. And this Lindblad engineering method is also applicable to suppressing other Markovian noise impacts. Finally, we want to mention that Lindblad engineering is more effective in optimizing quantum gate operations relying on complex control pulses. So this is the end of my presentation. Thank you very much.